Hi, my name is Mark, KB7GF, and today I would like to share with you a presentation that I delivered to the Dayton 2014 Hamvention. It was my first visit to the Hamvention, even though I'd been licensed since 1978. It was very enjoyable, but also a bit overwhelming. As I was preparing for this presentation, a book that I enjoyed reading many years ago came to mind. The book, written by Robert Fulghum, is called All I Really Needed to Know I Learned in Kindergarten. One reason I like this book is that it tells me what I should have learned in kindergarten. You see, I never actually went to kindergarten, so this is my way of catching up, sort of my own personal cliff notes of what I missed. If you haven't read it, the book provides some great insights to those simple truths that are simple yet powerful. Things like playing fair and not hitting people. But the reason it came to mind while writing this presentation is because of the first thing, the first aspect, the first idea in the book. Share everything. And that's what we're going to do today. As we talk about the shared apex loop, I want you to see that this simple concept of sharing everything can even apply to antennas, because the subject at hand today is the shared apex loop receiving antenna. And in this antenna, we share more than just the apex, much more. In fact, sharing is just the beginning, because in addition to the apex, we also have the loops that share the mast. We have signals taking turns sharing the delay line. We have loop signals sharing the combiner. The combined signals share the amplifier and optional filter. And power signals and data share the feed line. All this sharing enables simplicity and consistency, and a whole lot less duplication of effort. The net result is a directional wideband receiving antenna that has only one combiner, one amplifier, one delay line, and only one cable between the antenna and the shack. So today we're going to quickly explore the shared apex loop antenna by first of all looking at the goals and aha moments during the design, and then follow me as I describe briefly our journey to production. And after that we'll look at reviews of those that have tried the antenna and used it. We'll get some first-hand accounts, and then also variations. How can you change this? And all the different ways that it can be modified. And finally, we'll wrap up with some ideas on some paths to what I call Extreme RDF. So let's get started. First, our initial design goals. So starting with the end in mind, I had some specific ideas about what we needed in this antenna. I needed something that could fit in my small suburban yard and wanted to be as stealth as possible. It needed to be compact. It also needed to be directional. I wanted to be able to avoid interference and aim for signals. Signal to noise was important, and directivity is a great enabler. I also wanted it to be broadband because my roots were and are in shortwave listening, and I still enjoyed AM and shortwave listening DXing along with amateur radio. So I wanted something that could be directional over a wide range of frequencies. Ideal everything from the AM broadcast band all the way up to 10 meters. In addition, I just installed a ground-mounted vertical with 60 radials, and I didn't want to have to do that again, so I wanted it to be as ground independent as possible. And finally, I always liked the idea of electronic rotation, and so I wanted to include that also. So some of the aha moments were pivotal in really coming up with a design that would meet these design goals. One of the first ones that I realized was I needed a way to achieve the bandwidth goal, and in 1968, J.H. Dunlavey patented a broadband directional receiving antenna using only two elements, a delay line and a combiner. The technique is a true time delay method and is just what I needed. If you look in figure 1 in the slide, this method positions two identical elements a distance apart and introduces a time delay listed as TD on the slide. That time delay is applied to one of the signals from the element in the non-favored direction, and then subtracts the time-delayed signal from the non-delayed signal in the favored direction. The resultant pattern is a directional pattern over a wide range of frequencies. The elevation plots shown on the slide are for the smallest commercially available shared apex loop, the SAL-12, and it shows directivity from 500 kilohertz all the way to 28 megahertz. Another aha moment was the realization that it is possible to have a front-to-side rejection with only two elements when each of those elements are intrinsically bidirectional. The idea here is that we are letting the physics and wave mechanics do the heavy lifting. Now, loops were natural candidates for the elements since they are bidirectional. Their largely ground-independent nature is an added bonus and helped kill two birds with one stone. Another aha moment occurred when I found that the distance between the loops was much less a factor than the distance between the loop feed points. Let me say that again. The distance between the loops was much less a factor than the distance between the loop feed points. This opened up the possibility of bringing the loops very close together, in fact close enough for them to be spaced apart and supported by a single mast, so that the loops shared both the mast and the apex. Another aha moment was the realization that loop signals can be coupled using a current transformer made from a string of ferrite beads. This provided a great way to not only couple the signals, but also be able to position the coupler any point along the base of the loop. The original coupler is shown in the slide in the lower left, and a set of prototype couplers is shown on the right. We will use a red rectangular symbol for the couplers as a schematic representation throughout the remainder of this presentation. Another aha moment is that we can combine signals before amplification to reduce circuit complexity. You know, most receiving arrays utilize amplifiers at each element, and this is where I started in my early experiments. However, the loops provide an interesting opportunity here because they exhibit relatively low impedance, which enabled unamplified signals to be transported using short feed lines. This gave me the option of either having amplifiers before and after the combiner, or alternatively, simply after it. Positioning the single amplifier after the combiner elements eliminates the pesky task of phase and amplitude matching each amplifier. A further benefit comes because the lower frequency signals cancel more than the higher frequencies in the combiner. This provides an inherent high-pass characteristic, lessening the dynamic requirements of the amplifier. And if filtering is necessary, only a single filter is required, and it is positioned between the combiner and the amplifier. So I chose to have no active components before the combiner, favoring sharing and simplicity. And finally, another challenge was, what do I do with the delay? How do I achieve this time delay and have that time delay be independent of frequency? How do you provide a stable time delay over such a wide range of frequencies? For this design, I did choose to use the long-established coaxial delay line. But the challenge is that the delay line will only have a stable delay when it is terminated into its characteristic impedance. It is challenging enough to satisfy the requirement on the combiner side of the delay line if you are trying to provide wide bandwidth as well as low noise. But there's an added complication. How do you have the impedance controlled on the loop side where the impedance is uncontrolled? Thankfully, through experimentation, I was able to determine that for a receiving array, the delay accuracy can be maintained if the loop side impedance of the delay line is less than or equal to the characteristic impedance of the delay line, keeping, of course, the combiner side equal to the characteristic impedance. This finding also facilitated the single amplifier approach. Now, there is a downside. There will be a small amplitude imbalance if there is a mismatch on the source, that is, on the loop side. But this does not seem to have a material impact on the performance of the array, especially at low frequencies. Another aha moment comes the fact that signals from adjacent loops can be connected in parallel to provide the intermediate or in-between directions. I've found this through modeling, and it was proven very early on through experimentation. The resultant pattern tends to be a bit more broad, having less front to side, but has a great front to back ratio. So given all of those aha moments and given the design goals, I then set out to formulate the architecture for the antenna. So first we have 4 identical loops shown schematically here. In practice, these loops would be positioned around a single mast, and we see the combiners as the red rectangles. And then we have a switch assembly that connects to the 4 loops. The signals are routed through a series of loop relays, and signals are routed either directly to the combiner or through a delay line and then the combiner. Once the signals are combined, they exit to the amplifier. If a filter is required, the single filter would be inserted between the combiner and the amplifier. Then we have a single antenna to shack transmission line. This can simply just be a run of RG6. Notice that the power, data, and signal are all shared in the coaxial line. And finally, we have a controller which multiplexes the power and the data onto the transmission line and also provides a user interface as well as routes the signal to the receiver. So that's the basic architecture that we set out early on in the shared apex design, and is actually still what is being used in production. So where do we take these concepts and these ideas? We have some great concepts, but how do we turn it into something useful? I must admit that there's a lot more sweat and work involved in this process than I realized at the beginning. See the early version of the switch assembly without relays, and note that the delay line is actually the RG174 that's coiled up in the box. Next to that is a picture of the first shared apex loop. It's actually a 2-element rotatable version in my backyard. Once I had proved out some of the initial concepts and the modeling seemed to be working pretty well, I decided to file a patent application on the new design. So you might be wondering, why did I file a patent application so early in the project? Well, you see, I'm a patent agent by trade and would often encourage my clients to file patent applications early in their projects. This is a bit of a case of having to take my own medicine. And it was actually kind of painful to have to stop working on this exciting design to write the patent application, but we got it done. Then I also decided to write a QST and QEX article to share it with other amateurs and encourage them to experiment with the technology. There was a pretty long gap between the time that the articles were submitted and they were actually published. During that time, waiting for the articles to be published, I went through lots more iterations, especially on the amplifier. And the pictures here in the slide show some later versions of the switch assembly and the controller, as well as the base of the shared apex loop. Once I had working hardware, I made several YouTube videos and presented the concept at the Spokane, Washington Hamfest in September 2011. Finally, I had hardware in the form of an evaluation kit and a reference design that was ready to hand over to a company for testing and hopefully be incorporated into their product line. I contacted a number of companies looking for anyone that would be interested in taking on the product. After many inquiries, a number of conversations, there was really no interest. No interest, and it was a bit discouraging for a time. I had something that was working very well on my own station, and I couldn't get anybody else to take it on. So in my journal, I made an entry in March of 2012, and it said basically this: after several years of work on the design of the shared apex loop array, I have reached an unsettling conclusion. I have developed an answer to a question that nobody is asking. That was a discouraging time, and I was ready to give up on the project. I decided to make a few more inquiries, though, and at last found someone that was interested. Jay at Array Solutions answered my email within 15 minutes, and within 6 weeks he had his evaluation system up and running. His initial response was, "Wow, this thing really works." And that was an exciting time. The patent issued, and we signed an exclusive manufacturing and marketing agreement in early 2013 for Array Solutions to commercialize and market the shared apex loop. So Jay had the evaluation kits, but we needed to turn that into a production design. So we needed to make a few improvements. It was time for the design to grow up. Jay's team assisted greatly in this effort. I had optimized the array for shortwave listening, and it had good directivity but lacked sensitivity, especially on 160 meters. One way to improve the sensitivity was to supersize the loops. So we decided to double the original loops, which is what the SAL-20 is, and the SAL-30 is actually 3 times the original size of the original prototype. The controller also needed to grow up. It needed a better looking interface, and K7MI also added computer control via the Hamvention Shackland interface. The switch assembly is the unit that's mounted at the base of the antenna, and it's important to note that all of the electronics at the antenna are housed in this single enclosure that's mounted on the mast. The feed line connections enter the switch assembly from the bottom, and those are balanced feed lines that come from the loop couplers, which are positioned at each loop. Another great feature of the production design is the socketed amplifier. This provides an elegant upgrade path, and it future-proofs the design. The production amplifier is also better than any of the prototypes that I did because it has more gain and quite a bit less noise than the prototype versions. And in addition to that, the production version includes options for stuffing additional filters between the combiner and the amplifier. Oh yes, and there is also some hardware that comes with the antenna also. The mast, the loop wires, the couplers, etc. So let's put it together. Let's see what this looks like as we put it together. First, we have the mast. It's a non-conductive mast, and we orient the loops around the mast. And then we mount the switch assembly to the mast, and then slide the couplers out to the specific location specified in the manual. And then we connect the feed lines up to the switch assembly to each of the individual loops. And then we connect the delay line. And finally, we connect the feed line to the shack. Now we can also see the shared apex loop as it is operating as we turn the loops. The green loops are connected directly to the combiner, while the red loops are connected to the delay line and then to the combiner. Gray loops are unconnected for that specific direction. Notice the pattern as it rotates around the circle. Okay, that's all great, but what do people say about these that are actually using them? Do they work? Well, first production units have only been shipping since the fall of 2013, so we were still early in its introduction. However, there have been several published reviews as well as a number of eHamNet reviews. Let's look at a few of these to see what these guys are saying. For example, Carl K9LA says in his QST review that the shared apex loop achieves a good balance between performance and footprint, and it opens up the next level in receiving ability for low-band DXing and contesting efforts, and is especially attractive if limited space is a consideration. We also have N1DG, and he notes that the directivity is better than the K9AY. Brian N3OC observes a directivity between 15 or a front to back between 15 to 30 dB depending on the arrival angle. His review is in the February 2014 PVRC newsletter. We also have a picture that Bruce sent us, a very snowy picture, and he notes that he installed it when the temperature was 15 degrees above zero, and that the antenna works even in the snow, and the feed lines are not affected by the snow. We also see Thomas K8WDX posted a nice picture and says this thing is great, and likes the quick direction agility to be able to flip the directions back and forth and have the eight different directions that he can choose from. We also see KZ1X in the eHamNet review of the SAL30 says that this edition has changed the station for the better by a lot, and believes the shared apex will become the performance size benchmark for receive antennas. KN2M notes that the SAL30 easily outperforms the SAL20 on 160 meters, and says that this is the best listening antenna he's ever used. And N8BI finds that the shared apex eliminated 20 dB over S9 snow static. He also notes that the front to back ratio exceeds his expectations, and that the signal to noise ratio is better than the beverage. Roger K1DQV says his beverage is a bit better, but he only has one, so having the additional directions from the shared apex makes it worth the cost. We are glad that he's a happy low-bander. And finally, Jonathan W6GX provides this beautiful picture and says the results are fantastic. He's thankful that this is now available to everyone. So it looks like a few people are asking the question that we have answered with the shared apex loop. And while the majority of these early adopters are DXers and contesters, I think that any HF amateur and shortwave listener, for that matter, could benefit from the shared apex. One of the things that defines many amateurs is experimenting. Happily, the SAL is an experimenter's dream, providing many degrees of freedom. It is amazing that you can... It is amazing all the different things that you can do with the shared apex and with a free copy of the 4NEC2 antenna modeling software. There are many different combinations of coupler locations and delay line lengths that define how a shared apex will act in operation. We call these operating points, and we have an open shared apex loop Yahoo group where we make various operating point tables available for your use. The existing tables represent only a small sample of the possibilities. The RDF of the shared apex loop varies between 8 to 10 dB depending on the operating point. So here's an example. Notice how the null angle and the pattern changes with a different time delay. In practice, you can change this delay by changing the delay line length. Here we see a delay of 3 nanoseconds, 4 nanoseconds. As it gets larger, notice that the angle is lowering. And now we'll go back the other way, decreasing the delay. The angle is increasing, and it's becoming more bidirectional. Another thing that you can change is the coupler location. A position near the center but biased towards the mast provides the highest RDF at the expense of some forward gain. If you want more forward gain and can tolerate a broader pattern, move the coupler locations outward and increase the delay line length according to the operating point. To further show the pattern impact of a selected sample of operating points, we show this animation. The purple rectangles are, in this case, the couplers. And notice how the pattern changes as we move steadily towards the mast. Once again, moving from the outside to the inward, we reach an optimum, and then the pattern starts to broaden and actually goes broadside as we get it closer and closer to the mast. We can also change the loop sizes, just as we were able to in the going from the prototypes to the production. We can also change the aspect ratios, so you can make it taller or wider or shorter. It's just a matter of modeling to determine what the coupler location is and the delay time, so you can make the delay length. And also shapes. There's nothing magic about the triangle. You can use square loops, you could use round loops, you could use a diamond loop, you can use a inverted right triangle loop. Use your imagination. Once again, modeling is the key. So we've looked at some variations, we've looked at the paths to production, but how do we get more out of this antenna? What are some paths to get beyond that 10 RDF? And another aha moment in this design was the realization that using a single amplifier, using a single combiner, using a single delay line, we can actually achieve incredible RDFs, considering that you're only using one of each of those elements. So can a loop array actually do the pattern that's shown in the slide? Well, let's see. The challenge with any loop array is how do we address the backward pickup angle issue that is intrinsic to the loop? What do we do here? Recall that as we were watching the animation a few minutes ago and changing the time delay, we noted that the pattern becomes bidirectional as we have a null off the top of the antenna. When we have the time delay equal to 0 and the couplers in the middle of the elements, we have a pattern that looks a lot like a bidirectional vertical. We have the advantages of a loop combined with the advantages of a vertical. The combiner and the delay line in this case are actually unnecessary when the delay is 0. So to achieve that pattern, all we need to do is simply connect the feed lines from each of the individual loops in canceling relation so that the resultant signal is just essentially disconnected together. So there's no need for a combiner, there's no need for a delay line since the delay is 0. So armed with that, essentially a 0 delay element, we can take two of those 0 delay elements and we can connect those to our switch assembly, the same switch assembly that we use in any of the shared apex loops. And we add a 35 nanosecond delay line and we achieve 11.9 dB RDF on 160 meters as shown in the pattern. We can also take 4 of these loop pairs, connect them to the same switch assembly, the same one that's used on the SAL 12 and 20 and 30. And we can connect those as shown schematically in the slide, add our delay line, and achieve the following results: 11.8 dB RDF and 11 point, that's on 160, and 11.5 dB RDF on 80 meters. Now in this particular configuration, the forward gain on 160 will probably not be adequate. And so we have a few people experimenting with these, and we're looking at either increasing the loop size or using square elements to increase the capture area. But notice the pattern. That would be a very respectable pattern and an incredible thing to add to any listening station. There's more possibilities, many more possibilities for achieving these extreme RDF shared apex loop possibilities. One is, as shown, to go ahead and use the flat tops, what I call flat top loops, connected as shown there. As I mentioned, square loops are also a possibility for getting more forward gain. There's actually even a broadside mode that you can use if you have the couplers positioned very close to the center of each loop pair. So this has been quite an adventure for me, developing the shared apex loop, and it's been exciting to see the response from those early adopters who have given this new approach a try. Now developments are continuing, so I encourage you to visit the website listed on the slide, as well as join the Shared Apex Loop Yahoo group and join in the discussion. There's lots to be learned here. We are just beginning in many ways, and we'd love to have you come and join us as we really pursue this exciting new platform, a new way of thinking about receiving antennas. So in closing, I would like to thank those organizations and products that provided valuable support in this endeavor. 73 and Good DX.